Hello everybody, and welcome to this introduction to differentiation and integration. Okay, so this is going to be a fairly short introduction, but we're going to look at the derivative and the integral. Okay, now this is going to be a very, very brief introduction. We're not going to go into the nuances of limits, and we're only going to give a brief overview. Okay, so this video is built to give you the necessary information of some basic calculus to do some introductory calculus-based physics. Okay, so this is not going to be a video for mathematicians. This is a video for physics students to get a little bit of the machinery necessary to do some things with physics. So, to that end, we're going to start... That's terrible. We're going to start with the derivative, okay? And at the end of the day, the derivative is just a rate, okay? The derivative is just a rate. It relates how one variable will change with respect to another variable. In more technical language, it refers to how a function changes as one of its variables changes. Okay, the rate at which the function changes with respect to a given variable. Okay, we'll see what this means. So, to kind of give the motivation of the derivative is also the slope of a function. Okay? So when we take the derivative, we are taking the slope of a function, and we can either take the derivative of a function and just keep that result, or we can take the derivative of a function and then evaluate that result at a particular point. Okay? And we will do some examples of this. But to kind of motivate what the definition of the integral does, okay, suppose I have a function, and let's say that my function f of x is on my y-axis, and my independent variable x is on my horizontal axis. And we don't know what the function is yet. We'll define specific functions here shortly, but let's just say I have a function that's like increasing like this. Okay? And as you can see, okay, if we kind of look in this region right here, the slope, the slope of this red line is not as steep as here, and this part of the function is not as steep as up here. So this whole notion of taking a derivative is to evaluate what the slope of your function is at different points. Okay, so with that being said, I didn't want to erase the whole thing, but in any case, so suppose I want to know specifically, I'll call this point x0, and I'll call this point x1. Okay, and so the value f of x has these two values, okay, f of x1 and f of x2. And the slope is going to be, of course, the slope of a line between 2 points is equal to its rise over its run. Okay, so whatever the change in the vertical or the change along the vertical axis is between my 2 points divided by the change in the horizontal distance, then this gives me an estimate of the slope between these 2 points, right? But what you'll notice is that the slope between these 2 points doesn't necessarily fall right along this line. Okay, so when my points x0 and x1 are finite, okay, when they're somewhat distant apart, then the dashed line that's supposed to represent the slope, imagine that's straight, by the way. Okay, the red dashed line there, imagine that's straight. Then the wider delta x is, or the farther apart x0 and x1 are, the less accurately the red dashed line will fall along the black curve that actually represents the function. Okay, but to start, we say the slope of a function, the rise over the run. Well, the rise is the difference between my function values. And the run is the difference between my x values. Okay? So this represents delta y, and this represents delta x. Right? But to make things a little bit more accurate, right, what we actually want to end up doing is we want to, in order to get the red dashed line to fall right along the curve, what we want to do is we want to make this quantity small. And in fact, we want to make it infinitesimally small. I got to remember how to spell infinitesimally. Okay, we want it to be infinitesimally small. So what that means is we want to bring x1 as close to x0 as we possibly can until they're an infinitely small distance away from each other. And then I want to evaluate the function through those 2 points. And if we do that, so let's zoom in. Okay. Let's put now x1 right here. Let's shift it over. So this is my new x1, and then the distance between them is now going to be my new delta x. And now this looks a whole lot like a straight line, right? So if I zoom in on that function, in that region, I now have something that looks pretty close to a straight line. And when I measure the slope between these, okay, now that will be very, very close to being a straight line. And if I make the distance between x0 and x1 infinitesimally small, then it will be a straight line, right? As if I keep on zooming in on a curve, it will eventually become a straight line. And so the difference in my y values, again, is going to be the function evaluated at my second point minus the function evaluated at the first point. Okay, so we still have this, right? And we will still have delta x. Well, if we truly make this infinitesimal, okay, then here's what we do. Here's the way that math books would define this. Let your 2 points be infinitesimally far away, so that whatever your curve is, it's more or less a straight line. Pick a point x. I'm then going to move an infinitesimal distance along the x-axis to a new point x plus h. And we call this distance h. Okay? And now we have a straight line between our 2 points. And so the slope, let's see if we can actually sharpen that up a little bit. The slope along this line is going to be the function evaluated at my point just a little bit beyond my original point minus the point evaluated at the original point, then divided by the width between x and x plus h. So my new slope, slope doesn't have two e's. My new slope is going to be f of x plus h minus f of x divided by h. And without going too deep into limits, what we say is that the true derivative is in the limit, let me write that a little bit better, in the limit that h goes to 0. Okay, so here's where we're not going to be too formal with what the definition of what this is. But what this means is that this width we're going to let become very, very small, infinitesimally small, such that it is effectively 0. And then we'll see what happens. Okay, and when this condition is met, we evaluate this entire expression as h goes to 0. Then this isn't just the slope anymore, this is now the derivative. Okay, this is now the derivative. We call this f prime of x. And it's also written, take the differential of x divided, or the differential of f divided by the differential of x. df dx is the derivative of f with respect to x. And f is our function, remember. And x is our variable. So let's do an example here and see how this actually works. So let's let f, let's go ahead and let's make this f of x equals x squared. Okay, so let's see what happens if I take the derivative of f squared. So the derivative df dx is going to equal f of x plus h minus f of x Apologies, I forgot to turn off my air, and I don't need excess noise. So we're going to take f of x plus h minus f of x, and we're going to divide that by h in the limit that h goes to 0. Okay? So what is f of x plus h? Well, if f of x is x squared, then f of x plus h is going to equal x plus h quantity squared. So what this means is basically you just replace your argument everywhere there's an x, you replace it with an x plus h, and you then do whatever algebraic function needs to happen. Okay? Whether it is squaring something, multiplying something by a constant, taking the square root, whatever the case may be. Okay? So this is going to be x plus h quantity squared minus x squared divided by h in the limit that h goes to 0. Okay? So now we expand x plus h squared by foiling it, so this becomes x squared plus 2x times h plus h squared minus x squared divided by h, and once again in the limit that x goes, or not x but h goes to 0. Okay? And what you can see is that my x squared, everything in the denominator, I can now add, subtract, so on. So I have an x squared minus an x squared, and then I have a 2xh plus h squared over h, and in the limit that h goes to 0. And so when I divide by h, I now have 2x plus h in the limit that h goes to 0. And if h goes to 0, then I'm just left with 2x. Okay? So this is the most important result. The derivative of x squared, we also write the derivative like this. If you want to write out the entire function, d dx, I'm going to take the derivative of x squared with respect to x. That's what this notation means. And it's the exact same notation as df dx. The derivative of f with respect to x is just 2x. Okay? So this leads to what is known as the power rule. And this is the most important rule in differentiation. Okay? If you have a function that is some constant times x to some exponent, okay? Then your result you'll notice, okay, the relationship between x squared and 2x. 2x is the same thing as 2 times x to the 1. Okay, 2 times x to the first. So what we've effectively done is we've taken the exponent and brought it down front, and then we've subtracted 1 from the exponent. Okay? So your derivative is going to be whatever your original coefficient was times your original exponent, and then your variable x is just going to be raised to a new exponent that's 1 less than what it was before. So for example, let's do like 3 explicit examples here. let's say I have 3x cubed. The derivative of this, bring your power down. So that's going to be 3 times 3 times x to the 3 minus 1, or x squared. So this is the same thing as 9 times x squared. Right? If I have 2 times x to the 4th, then the derivative of that is equal to 8 times x cubed, right? Bring your power down, multiply, and then subtract 1 from your exponent. And if I have, let's say, 3 times x to the 10th, okay? Then the derivative of this would be 30 times x to the 9th. Okay. Now it also happens that if you have a polynomial expression, something like ax squared, let's say a quadratic, plus bx plus c, okay, and I want to take the derivative of this, then I just take the derivative of each term and keep my addition or subtraction signs where they are. Okay? And so the derivative of my first term would be 2ax plus, if I have x to the first power, then I bring that power down. And this is the same thing as b times 1 times x to the 0. And c is a constant, so c doesn't have any x dependency on it, and therefore the derivative of constants is 0. Actually, I shouldn't put an exclamation point there because I don't want to give you the impression that it's a factorial. Okay. And remember that anything to the 0th power is 1. So this is the same thing as b times 1 times 1, which is the same thing as b. So this is just 2ax plus b. Okay. So, for example, if we had a quadratic that looks like this, and I want to take the derivative, f prime of x, or df dx, the notation means the exact same thing. This would be 6x plus 4. All right. And so this is by far the most important rule. All right. This is by far the most important rule, is this power rule. Now, that takes care of polynomials. Now, there are some very special functions. So, for example, what is the derivative of special functions? Okay. So, for example, if I have a sinusoidal function, well, actually, I won't go here yet. We'll just leave this as x. And as a matter of fact, let's leave this coefficient out front. Let's just make this sine x. Okay, if I have sine of x, then the derivative of that is going to be cosine of x. I'm not going to go through the proofs here. You'll do this in your calculus classes. I just want to give you the results so you know them, so you'll have them if you need them for the physics. All right. The derivative of cosine is equal to negative sine. If I have an exponential function, then its derivative is actually itself. The derivative of e to the x is e to the x. And finally, the other very special function that we really need to be worried about that might crop up is the logarithmic function. So if I have the natural log of x, then the derivative of the natural log of x is 1 over x. Okay, so you can derive these using the original definition of the derivative. Okay, this is definitional. So really, in that sense, this could be a 3-liner because it's a definition. And you can derive the results I just gave you using this, but for the special functions, you actually have to do some particular expansion techniques to get the x plus h. And so we're not going to worry about those. We're just going to hand you the results. Now, there's an extra piece of this called the chain rule. And the chain rule says, well, what if I have a composite function? Okay, so here we have something like this. Okay, so here I have a sine function, but I also have a function 2x. So this is a function within a function. How do I take the derivative of a function within a function? Well, what the chain rule says is if I want to take the derivative of this, then what I do is take the derivative of the first function. So I'm going to take the derivative of the sine, and I'm going to leave the argument alone. I'm going to leave the argument whatever it is, but I know the derivative of sine is cosine. So the first step is that this is going to be the cosine of 2x. I've left the argument alone. And then I take the derivative inside, which is 2, and I multiply the two together. So this is 2 times the cosine of 2x. Okay, so the derivative of sine 2x is 2 times cosine 2x. And you can get more exotic functions, no doubt. For example, what if I have f of x equals 3 times sine 2x plus 4 ln times x. Okay, if I want to take the derivative of this function. So remember, plus signs are left alone, so I'm going to take the derivative of this, and then I'm going to add it to the derivative of this, and I can take them both individually. And so what I'm going to do is I'm going to take the derivative. Now the derivative of 3 gets left alone, right? It's a constant, so it gets left alone when it's a multiplicative factor. If it were by itself, its derivative would be 0. So this is going to be left alone, and this is going to be 3 times the cosine of 2x times 2 for the derivative inside the argument, plus 4 times the derivative of ln x, which is 1 over x. So this is going to be equal to 3 times 2 is 6. Cos plus 4 over x. Okay? Okay, so that will get you started on the derivative. Okay, there are more nuanced things. Actually, I will make one more note here, and that there's another rule called the product rule. And there's another rule called the quotient rule, but in fact, you can derive the quotient rule from the product rule. So if you know the product rule, you actually know the quotient rule, or at least can get it. So I'm not going to go into the details of the quotient rule, but we will mention the product rule. And the product rule says if I have a composite function, so let's say my function f of x is actually two functions multiplied together, say g of x and p of x, okay, whatever they might be. And so let's say that let's let g of x, for example, be 3x, and p of x is equal to sine of 2x. Okay, so in this example, f of x is going to be equal to, well, let me state what the rule says, and then we'll do the example. So the rule says that if you have two functions multiplied together, then the derivative of those two functions is equal to the derivative of the first times the second plus the first times the derivative of the second. Okay, so in this case, f prime of x would be g prime. The derivative of 3x is going to be 3 times the original function of p, and then I have my original function for g, and then I'm going to multiply that by the derivative of p. And the derivative of p is sine 2x times 2. I'm sorry, cos 2x times 2. Okay, so this is going to be the same thing as 3 times sine 2x plus 6x cos 2x. Okay, so that is the product rule. That's pretty much it for differentiation. This is the this is the most important rule to remember. Okay, that when we take the derivative of something, we're just going to bring down the power if it's a polynomial, which it very often will be for a lot of our purposes. That's why this rule is so important, because it's the one we will encounter the most often until we get to sound waves, oscillations, and things. This will be the rule that we follow the most. And by that point, if you haven't completed calculus yet, but you're in the calculus course, then it will be, you'll have done this several times over. You'll understand exactly what's going on. So that brings us to the integral. Okay, so the integral does the opposite of what differentiation does. In fact, sometimes it's referred to as the antiderivative. Okay. Whoop. Sometimes it's referred to as the antiderivative. So the integral, what an integral does, okay, instead of evaluating a function at 2 points and then taking the slope, what an integral does, okay, if I have a function like this, what an integral does is an integral adds. Okay? An integral represents a sum. All right? And what it really represents is an area under a curve. Okay? So an integral represents an area under a curve, but the process of integration is exactly opposite of what you do when you differentiate. Okay? So if you can figure out a function, let me rephrase. If you are tasked with taking an integral, the very first thing you want to do is ask yourself, is the function that I'm trying to integrate, is it a result of differentiating a function? If so, you can reverse engineer that differentiation and you can then find the integral. And that is the bulk of integrating. Okay. Now there's a lot of individual special techniques to arrive at those things because a lot of your functions may not be obvious what the original function was, and there's a lot of different techniques to find those. There may be the case where your function doesn't have an original function that you took the derivative of or could take the derivative of. There are a lot of functions that are said to be non-integrable. They don't have a function whose taking their derivative equals that function. And when that's the case, if you want to actually integrate, you usually have to do some sort of numerical analysis with a computer. But for the moment, we're going to avoid that. Okay. But what an integral does, let's say I am going to look at 2 points, once again x1 and x2, and I look at the shaded region here. Okay, the integral will find the area of that shaded region. Okay, and so what we do when we integrate, we use kind of an S-looking shape and say, I want to integrate f of x. And I have to integrate it with respect to a given variable. So this dx represents a differential variable, and it represents the exact same thing that the dx in dx represents. Okay, this dx represents the infinitesimal length along the x-axis, or the variable that you're differentiating with respect to. And so when you're integrating, you're saying, okay, I'm going to multiply my function here at some point, and then I'm going to multiply that by some width dx, and length times width represents an area. Okay, and then I multiply, then I find my next f of x, and I multiply that by dx again, and a very small width, and I find the next area. And I keep doing that process, and that is when I complete doing that process across the entire interval that I'm looking at, then I will eventually obtain the entire area under the curve here. So the integral represents just taking sums. But if my dx is truly infinitesimally wide, okay, technically, I guess I should have mentioned this, But this whole h, where we let h be a really, really small width along the x-axis, that is what dx also represents. Okay, dx is the same thing as h. Right? So what this says is evaluate your function at a given point, multiply it by a really, really tiny width to get an area, and then the integral sign says do that for an entire given interval, and then that will represent the sum of all of the little tiny areas that you have calculated. Okay. And so what this means is we have two types of integrals. We have an indefinite integral, and we have a definite integral. Okay, so an indefinite integral means there are no limits, no x0 and x1 that you're taking the integral with respect to. You're just finding the antiderivative of a function. You're just finding whatever function represents taking the derivative of the function that you find represents the function you are taking the integral of. I know that's a heck of a sentence, but this is just the antiderivative. Okay. Your definite means evaluate your integral between two specific points. Now, one of those points could be infinity, or in fact both of those points could be infinity. Technically what we would do is say negative infinity to infinity, but there are times when you're going to want your upper bound to be infinity. Okay, but infinity is a specific point from a mathematical point of view nonetheless. Okay, now let's just do some examples and kind of dive in here. So let's say I want to take the integral of x squared. Okay, so I want to find a function that when I take the derivative of, I get x squared. So if I want to take the antiderivative of this, I basically have to find the function that when I take the derivative of will give me x squared. Well, if I come up here, come back to the power rule, if I have a function that's of this form, then the antiderivative will be in this form. So what that means is I want to add 1 to my exponent to go from here to here, and then I'm going to divide by that new exponent. So when I have the power divided by the new power, I recover just a times x to the n. So doing that, adding 1 to my power, and then dividing by my new power gives me this. And we can see that if my original function f of x was indeed x cubed over 3, that taking the derivative of this is the same thing as 1/3 times 3 times x squared, which in fact is of course x squared. So that's great. Now there's one extra point about indefinite integrals, and that is we always have to add a constant. Okay? And this is because the derivative of a constant is 0, so there can always be a constant at the end of a polynomial chain, or really any function. There can be a constant at the end of it with a plus sign, and the derivative of this will always be 0. So when I take the antiderivative, I don't know if there was a constant hanging out there or not. So we always just add one obligatorily. Okay? So the official result for the indefinite integral of x squared dx is x cubed over 3 plus c. Okay. Let me write that a little bit cleaner. If we have the integral of, let's say, x cubed plus 2, okay, and I want to find the indefinite integral of this, then do the power rule on each term. Whoop, I need the dx. I need to know what variable I'm integrating with respect to. And so for the x cubed, I'm going to add a power. I'm going to add 1 to the power and then divide by that new number. And then I'm going to take the 2, and this is the same thing under the integral sign as 2 times x to the 0. Okay? So if I have x to the 0th power, then if I add a power, this becomes 2x, and then I have to add the constant because I don't know if there was a constant hanging out or not. All right? And once again, we can see that this is in fact the integral. If my original function was indeed x to the 4th over 4 plus 2x plus c, then if I take the derivative, then bring my first power down, 4 over 4 times x cubed plus 2 times 1 times x to the 0 plus 0, since the derivative of a constant is 0, and this becomes x cubed plus 2, which is the function that I was taking the integral of originally. So these agree. Okay, so integration actually has the advantage that in many cases, if not most cases, you can check your result by taking the derivative of your result of your integration. And that will help you check and make sure that you've done your integration properly. Okay? So, to that end, some integrations of special functions. Okay. Some integrations of some special functions. Well, the integral of cosine x dx is equal to sine x. The integral of negative sine x is cosine x. The integral of e to the x is e to the x, and the integral of 1 over x is equal to ln x. Now, I should mention that 1 over x is the only power for which the integration, the power rule on the integration and differentiation doesn't work. Okay, 1 over x, I can differentiate 1 over x, but I can't integrate 1 over x using the power rule, because this is the same thing as saying x to the negative 1 dx, and that would be equal to, if I used the power rule on this would be negative 1, bring that, I don't want to bring that down. I want to add, so this would be x to the negative 1 plus 1 over my new power, which is 0. So this is x to the 0 over 0, and of course that is a bad result. So the fact that you would end up dividing by 0 here means that this is not a valid thing that you want to do. So that's why you cannot use the power rule here. Okay. All right. So last thing is to talk about definite integration. And definite integration says what if I take the derivative or take the integral of a function, and let's actually do an explicit example here. Let's say I have the function f of x equals x squared. And I want to calculate the area under the curve between x equals 1 and x equals 3. Okay? So I want to calculate the area inside that box represented by this shaded region here. Okay? I want to calculate the area under that curve. Right? So what we do is we write our integral sign, and the function we're going to integrate, our integration variable that we're going to integrate with respect to, and then our limits go on the ends of our s here. So this is going to be from 1 to 3. Okay? So here's what this means. Take the antiderivative as you normally would, and so this is going to be x cubed over 3, but instead of adding that obligatory plus c, what we do is we now say that we're actually going to evaluate this expression from 1 to 3. Okay, so this line with the numbers at the bottom and top means evaluate this function from 1 to 3. So what we're going to do, what this means is that I'm going to plug in my top value or my upper limit in for my x value. And then I'm going to subtract the result of plugging in my lower limit in for x. Okay, so definite integrals say find your antiderivative, evaluate your function at your upper limit, evaluate your function at your lower limit, and then take the difference between the two. Okay, so this is going to be 9/3 minus 1/3, or 8/3. So the area under this curve is 8/3. That's what this represents. Okay. Let's do another example here. So let's evaluate the cosine function from 0 to pi halves. Okay. That's a terrible pi. That's a much better pi. So if I want to integrate cos x dx, come back to our list of results, and the integral of cos x dx is sine of x. And I'm going to evaluate that from 0 to pi halves. So this is going to equal the sine of pi halves minus the sine of 0. And if we assume that we're in radians, which these measurements are radian in nature anyway, So it's a very, very safe assumption. The sine of pi halves is, of course, 1. The sine of 0 is 0. So the area under a sine curve, if I look at one cycle here, the area 0, pi halves would be here, and pi would be here. 3 halves pi would be here, and 2 pi would be here. So the area of this shaded region right here, the area of that shaded region is equal to 1. Okay? That's what that result is telling you. The area of that shaded region is 1 if this is x and if this is f of x. Okay? So, those are the major tools that you will need. Everything else that might crop up, you'll get in your calculus classes. But these are the two major things that we're going to need sooner rather than later. So that's why I wanted to put these in front of you. And if you have questions, you can always ask me in class. And we will see you in the next lecture.